Welcome! In this session, we'll tackle LeetCode problem number 486, Predict the Winner. This is an exciting challenge where we'll explore strategic decision-making in competitive programming. Let's dive in and break it down step by step. In this problem, you are given an array nums of non-negative integers. Two players take turns selecting numbers from either the beginning or the end of the array. The goal is to maximize the total score for each player, and the player with the higher total score wins the game. If both players end up with the same score, the first player is considered the winner. Now, the key assumption here is that both players play optimally, meaning they will choose moves that maximize their own scores while minimizing their opponent's chances of winning. Your task is to implement the function predict the winner, nums, which returns true if the first player is guaranteed to win under optimal play, or false otherwise. The input is an array of integers, and the output is a Boolean value indicating whether player 1 can secure a win. Let's look at a few examples to understand this better. In the first example, we have nums equals 1, 5, 2. Player 1 can choose either the first number, 1, or the last number, 2. If player 1 picks 1, player 2 will optimally take 5, leaving player 1 with the remaining 2. This results in player 1 having a total score of 3 and player 2 having 5. Alternatively, if player 1 picks 2, player 2 will still take the 5, leaving player 1 with 1 and the same total of 3. In either case, player 2 ends up with a score of 5, which is higher than player 1's score. Therefore, the function returns false because player 1 cannot guarantee a win in this scenario. In the second example, the array is nums equals 1, 5, 233, 7. Here, player 1 has a few strategies to consider. If player 1 picks 1, player 2 will take the maximum available value, which is 233. Player 1 can then take 7, resulting in a total score of 8 for player 1 and 238 for player 2. Similarly, if player 1 picks 7, player 2 will still take 233, leaving player 1 with a total of 12 and player 2 with 234. However, player 1 can play optimally by choosing 233 on their first turn. This forces player 2 to take either 1 or 7 on their turn, leaving player 1 in a position to maximize their remaining score. By playing optimally, player 1 can ensure a higher total score and secure the win. As a result, the function returns true. In the third example, we have nums equals 10, 20, 30, 40. Here, player 1 starts by taking the largest number, 40. Player 2 then chooses 30, which is the next largest value. On player 1's second turn, they take 20, leaving player 2 with the remaining 10. After all numbers are selected, player 1's total is 40 plus 20 equals 60, while player 2's total is 30 plus 10 equals 40. Because player 1 has the higher score, they win the game. Therefore, the function returns true in this case. Now, let's review the constraints and some edge cases. The length of the array, nums, is between 1 and 20, and each element in the array is a non-negative integer less than or equal to 10⁻7. For edge cases, if the array contains only one element, such as nums equals 5, player 1 wins by default since they take the only number available. If the array has two elements, like nums equals 10, 20, player 1 will always choose the larger number, guaranteeing a win. When all elements are equal, such as nums equals 4, 4, 4, 4, the total score is evenly split, and player 1 is declared the winner in the event of a tie. Finally, for large arrays or values close to the constraints, the solution must handle these efficiently to avoid timeouts or memory issues. With these considerations, you'll be better equipped to tackle this problem successfully. When tackling the predict the winner problem, the most intuitive approach is brute force. Here, we simulate all possible moves for both players. On each turn, a player has two choices. They can either take the first or the last element of the array. The game continues recursively with the remaining subarray, aiming to maximize the current player's score while minimizing the score of their opponent. This approach models the problem's recursive nature effectively, as it evaluates all potential outcomes based on these two choices. However, there's a major drawback: this method is computationally expensive. Since we explore all possible combinations of moves, the time complexity grows exponentially, specifically O(2 to the power of n), where n is the size of the array. This makes it impractical for larger inputs. To address this inefficiency, we consider a more optimized approach, dynamic programming. By leveraging DP, we avoid redundant calculations and systematically compute the optimal score for each subarray. In the dynamic programming approach, we define dp, I, j, as the maximum score a player can achieve when considering the subarray from index I to j, assuming both players play optimally. On any turn, the current player has two choices: pick the number at the start of the subarray, nums, I, or the number at the end, nums, j. The score for each choice is calculated by subtracting the opponent's best achievable score from the value of the number chosen. This is represented by the recurrence relation, dp, I, j, equals max, nums, I, dp, I plus 1, j, nums, j, dp, I, j1. To implement this, we use a 2D dp table of size nxn, where n is the length of the array. The base case is straightforward: when the subarray contains only one element, dp, I equals nums, I. We then fill the table for subarrays of increasing lengths, building up to the full array. The final result, which represents the maximum score the first player can achieve, is stored in dp, 0, and 1. This approach has a time complexity of O, n squared, as we fill an nxn table, and a space complexity of O, n squared, for storing the table. To further optimize space usage, we can observe that each dp, I, j, value depends only on the current and previous rows. By using a 1D array to store intermediate results, we reduce the space complexity to O, n, while maintaining the same time complexity. The dynamic programming approach stands out as the most practical strategy for solving this problem. While the brute force method provides a helpful conceptual foundation, its exponential time complexity renders it infeasible for larger inputs. By contrast, the DP approach leverages the recursive structure of the problem to compute optimal outcomes systematically, avoiding redundant calculations. Additionally, the space-optimized version of DP further enhances the method's practicality, reducing memory usage while retaining the same O, n squared, time complexity. This balance between performance and simplicity makes dynamic programming the ideal solution. It ensures that the approach is not only computationally efficient but also scalable, making it a strong candidate for both competitive programming challenges and real-world applications. To solve this problem, we need to focus on maximizing the score for the first player while ensuring that both players make optimal moves. The array represents the values or scores available for selection, and each player can only choose from either the first or last element of the remaining array. Our goal is to determine the maximum score the first player can achieve. The first step in tackling this problem is to define the problem state. Since the decision at each step depends on the current portion of the array under consideration, we define the state using two indices, left and right, which represent the boundaries of the subarray. At any point, the player has two choices: to pick the first element at left or the last element at right. This recursive structure will allow us to evaluate the outcomes for all possible choices. Now, for the base case, if left equals right, it means there's only one element left in the array. In this case, the player simply picks that element, and the game ends. This gives us a clear starting point for our solution. When we expand this further, the recursive relation comes into play. For a given state, left, right, if the player picks the element at left, the opponent then plays optimally on the subarray, left plus 1, right. The score for the current player is calculated as the value of the chosen element, nums, left, plus the difference between the remaining sum of the subarray and the opponent's score from their optimal play. Similarly, if the player chooses the element at right, the opponent plays optimally on the subarray, left, right 1, and the current player's score is calculated accordingly. The goal for the current player is to maximize their score, so we take the maximum of these two results. This is captured by the formula, dp, left, right, equals max, score underscore left, score underscore right. This recursive relation forms the backbone of our algorithm, as it systematically evaluates the best possible outcome for the current player at every step. To make this recursive approach efficient, we use memoization to avoid redundant computations. By storing the results of previously computed states in a 2D DP table, dp, left, right, we ensure that each state is calculated only once. This optimization significantly reduces the time complexity of the solution. Once memoization is in place, the next step is to initialize and solve the problem. We start by creating the DP table, where each entry DP, I, J, represents the maximum score the current player can achieve for the subarray, I, J. We then solve for smaller subarrays, such as those of length 1, and incrementally expand to larger subarrays, leveraging the recursive relation at each step. Ultimately, the answer for the entire array is stored in DP, 0, and 1, where n is the length of the array. Key insights include the optimal substructure of the problem, as each choice splits the problem into smaller, independent subproblems, and the symmetry in choices, where decisions depend only on the remaining subarray. By using dynamic programming, we reduce the time complexity from exponential to polynomial, making the solution both efficient and scalable. The implementation requires specific data structures to support the algorithm. The primary structure is the 2D DP table, which has dimensions n(x)n to store results for all possible subarray states. This allows us to retrieve results in constant time, O(1), for any previously computed state. Additionally, we can use a prefix sum array to further optimize the computation of subarray sums. This enables us to calculate the sum of any subarray, I, J, in constant time, avoiding redundant calculations. Let's examine the complexity of this approach. The time complexity is O(n²), because we solve O(n²) subproblems, and each subproblem takes constant time to compute. The space complexity is also O(n²), due to the DP table, with an optional O(n) overhead if the prefix sum array is used. It's important to consider edge cases as well. For a single element array, the result is simply the value of that element. When all elements are equal, both players achieve the same score. For an empty array, we return 0, as there are no elements to pick. And for large arrays, we ensure that the O(n²) complexity remains efficient within the problem's constraints. The pseudocode for this implementation begins with initializing the DP table. Each diagonal entry, DP, I, is set to the corresponding element in the array, as these represent subarrays of length 1. We then solve for larger subarrays by iterating over increasing lengths. For each subarray, left, right, we calculate the scores for both choices, picking the element at left or the element at right. The score from picking the left element is the value at nums, left, minus the opponent's best score for the remaining subarray, left plus 1, right. Similarly, the score from picking the right element is the value at nums, right, minus the opponent's best score for the subarray, left, right 1. We store the maximum of these two scores in DP, left, right. After filling the DP table, the result for the entire array is found in DP, 0, and 1, which we return as the maximum score the first player can achieve. This completes the algorithm, providing an efficient and structured solution to the problem. This solution implements a dynamic programming approach to solve the predict the winner problem. The function predict the winner uses a recursive helper function DP with memoization to determine the maximum score difference player 1 can achieve over player 2. The key idea is to simulate the optimal choices both players can make when picking elements from the array. We use memoization with the memo dictionary to store the results of previously computed subproblems. This avoids redundant calculations and ensures the algorithm runs efficiently. The DP function takes two parameters, start and end, which represent the current segment of the array being considered. The base case is when start equals end, meaning only one element is left. In this case, the score difference is simply the value of that element. For other cases, the function considers two scenarios, picking the first element, nums, start, or the last element, nums, end. The score difference is calculated based on the choice and the resulting subproblem. The goal is to maximize the score difference, so the function returns the maximum of the two possible choices. Finally, the main function checks if the maximum score difference for player 1 is non-negative. If it is, player 1 can either win or tie, and the function returns true. Otherwise, player 2 will win, and the function returns false. This approach has a time complexity of O(n²), due to the memoization table, and a space complexity of O(n²), for storing the results. Here we start implementing the solution in Java. The method predict the winner takes an array of integers, nums, which represents the numbers in the game. To solve this problem efficiently, we use a memoization technique to store the results of subproblems. This is done using a hash map called memo, where the key is a string representing the range of indices, and the value is the computed result for that range. Next, we define a helper function dp that takes two parameters, start and end, which represent the current range of indices we are considering. If start is equal to end, it means there's only one element left in the range, so the maximum score difference is simply the value of that element. Otherwise, we construct a unique key for the current range and check if the result for this range is already stored in the memoization map. If it is, we return the stored result to avoid redundant calculations. The main logic is then defined. The player can either pick the element at the start of the range or the end of the range. If the player picks the start, their score is the value of num's start minus the result of the opponent's turn, which is computed by recursively calling dp for the range start plus 1 to end. Similarly, if the player picks the end element, their score is num's end minus the result of the opponent's turn for the range start to end 1. We then take the maximum of these two scores to ensure the player gets the best possible outcome for this turn, store the result in the memoization map, and return it. Finally, we complete the implementation by returning the result of the helper function dp for the entire range of the array, from index 0 to nums.length 1. The main idea here is to analyze the score difference between player 1 and player 2. If this difference is greater than or equal to 0, it means player 1 can secure a win or at least tie the game, as they will not lose by the end. Thus, we return the result of the condition dp 0 nums.length 1 equals 0. This ensures that our solution dynamically calculates the best possible outcome for each player at every step, leveraging memoization to optimize repeated subproblem evaluations and achieve an efficient overall solution. To solve that predict the winner problem, we start with the input array nums equals 1, 5, 2. The goal is to determine if player 1 can win, which happens if the maximum score difference between the players is non-negative. To achieve this, we use a recursive helper function dp I, j, which calculates the maximum score difference player 1 can achieve from the subarray nums I, j. The memoization table memo helps store intermediate results to avoid redundant calculations. We initiate the process with dp 0, 2, since the full array spans from index 0 to 2. At this stage, player 1 has two options: pick either the first element, nums 0 equals 1, or the last element, nums 2 equals 2. If player 1 picks nums 0, the score difference is nums 0 dp 1, 2, which evaluates to 1 dp 1, 2. On the other hand, if player 1 picks nums 2, the score difference becomes nums 2 dp 0, 1, or 2 dp 0, 1. These two scenarios set the stage for solving the subproblems dp 1, 2, and dp 0, 1. Now we dive deeper into solving the subproblems. Let's start with dp 1, 2, which evaluates player 2's best response when the subarray is 5, 2. Player 2 can pick either nums 1 equals 5 or nums 2 equals 2. If player 2 picks nums 1, the score difference is nums 1 dp 2, 2, which calculates to 5, 2 equals 3. If player 2 picks nums 2, the score difference is nums 2 dp 1, 1, resulting in 2, 5 equals dash 3. Player 1, aiming to maximize the difference, would consider the maximum of these two outcomes, which is 3. Thus, we store memo 1, 2 equals 3. Next, we solve dp 0, 1 for the subarray 1, 5, where player 2 can pick nums 0 equals 1 or nums 1 equals 5. If player 2 picks nums 0, the difference becomes nums 0 dp 1, 1, or 1, 5 equals dash 4. If player 2 picks nums 1, the difference is nums 1 dp 0, 0, which evaluates to 5, 1 equals 4. Player 1's best choice is the maximum of these, resulting in 4, so we store memo 0, 1 equals 4. With these subproblems resolved, we calculate the result 4 dp 0, 2. If player 1 picks nums 0, the difference is 1 dp 1, 2, which equals 1 3 equals dash 2. If player 1 picks nums 2, the difference is 2 dp 0, 1, which equals 2, 4 equals dash 2. The maximum of these two outcomes is dash 2, so we store memo 0, 2 equals dash 2. Since dp 0, 2, 0, player 1 cannot win, and the output is false. In the second example, nums equals 1, 5, 233, 7, we use the same recursive approach with memoization to determine if player 1 can win. We begin with DP 0, 3, where player 1 can pick either nums 0 equals 1 or nums 3 equals 7. This leads to solving subproblems like DP 1, 3, and DP 0, 2. Using memoization, we avoid redundant calculations and store intermediate results such as DP 2, 3 equals 226, DP 1, 2 equals 228, and DP 0, 1 equals 4. With these values, we calculate DP 0, 3. If player 1 picks nums 0, the score difference is nums 0, DP 1, 3, which evaluates to 1, minus 221, equals 222. If player 1 picks nums 3, the difference is nums 3, DP 0, 2, resulting in 7, minus 225, equals 232. The maximum of these two outcomes is 232, so DP 0, 3 equals 232. Since DP 0, 3 equals 0, player 1 can win, and the output is true. In the third example, with nums equals 7, 8, 8, 7, we follow the same recursive and memoization strategy. Player 1 can strategically play to either win or force a draw depending on the choices made by player 2. After evaluating all possible scenarios and using memoized results for efficiency, we find that player 1 has a winning or drawing strategy. Therefore, the final result is true. The time complexity of our solution is O, n squared, where n represents the length of the input array, nums. This is due to the recursive helper function, dp, start-end, which calculates the maximum score difference for every possible subarray defined by the indices start and end. The key factor here is that the number of unique subarrays is n asterisk, n plus 1/2, a result of summing the first n integers. This simplifies to O, n squared. For each unique subarray, the function performs a constant amount of work to compute the values pick_start, pick_end, and update the memoization table. Thanks to memoization, each subarray computation is performed only once, avoiding redundant calculations. As a result, the overall time complexity across all cases best, average, and worst is consistently O, n squared. The space complexity of this solution is also O, n squared, primarily due to the memoization table and the recursion stack. First, the memoization table stores results for all possible subarray ranges, start and end. Since there are n asterisk, n plus 1/2 unique subarray combinations, the space required for memoization is O, n squared. Additionally, the recursion stack contributes to the space usage. The depth of the recursion tree corresponds to the size of the input array nums, meaning the recursion stack can grow up to O, n in the worst case. However, this O, n space usage is negligible compared to the O, n squared space required by the memoization table. Therefore, the overall space complexity remains dominated by the memoization table, resulting in O, n squared. A comparison between the naive approach and the optimized solution highlights the efficiency of using memoization. In the naive approach, the function explores all possible ways the two players can pick numbers from the array. With each pick, it recursively solves subproblems for the remaining array. This leads to an exponential time complexity of O, 2 to the power of n, as there are 2 to the power of n possible ways to pick numbers. In contrast, the optimized approach leverages memoization to store results of overlapping subproblems, eliminating redundant computations. This reduces the time complexity to O, n squared, which is a dramatic improvement. Mathematically, the time complexity arises because there are O, n squared, unique subproblems, and each takes O, 1, time to solve. Similarly, the space complexity is O, n squared, with the memoization table dominating any additional space, such as the recursion stack. To summarize, the optimized approach for this problem achieves a time complexity of O, n squared, and a space complexity of O, n squared. By utilizing memoization, it significantly improves upon the naive approach, which has an exponential time complexity of O, 2 to the power of n. This optimization transforms the problem into one that scales polynomially, making it far more efficient for larger inputs. One common mistake when tackling this problem is overlooking the base cases in recursive solutions. For example, when the array is empty or contains only one element, failing to account for these edge cases can lead to unexpected runtime errors, such as index out-of-bounds issues. Another frequent pitfall is not optimizing recursive calls. A brute force approach might repeatedly calculate the same subproblems, which results in exponential time complexity. This is why using memoization or shifting to a dynamic programming approach is critical for efficiency. Additionally, ignoring the input constraints can lead to inefficient solutions. If the problem specifies bounds, like values between 1 and 10,000, understanding these constraints can help you design an approach that avoids unnecessary computations. Lastly, it's important to correctly interpret the problem's objective. In game theory problems like this, players aim to maximize their own score while minimizing the opponent's. A common mistake is focusing solely on maximizing your score without considering the optimal moves your opponent might make. Similarly, relying on a greedy approach, such as always picking the largest available number, often fails because it doesn't account for future outcomes. These mistakes highlight the importance of a strategic and holistic approach to solving the problem. Now, let's delve into some insights that can help you perform well in interviews. A key concept in many game theory problems is the idea of optimal substructure. This means the problem can be broken down into smaller subproblems, and solving these systematically allows you to build the overall solution. Dynamic programming is an excellent tool for leveraging this property, as it enables you to store and reuse previously solved states. Another important aspect is pattern recognition. These problems often require you to minimize your opponent's advantage, which means thinking 2 steps ahead. If you make a particular move, what will your opponent do in response? Additionally, be prepared to discuss time and space complexity during interviews. While a naive recursive solution might have exponential complexity, dynamic programming can reduce this significantly, often to O(n)². Finally, clear communication is vital. Walk your interviewer through why your approach is optimal, especially with respect to the given constraints. Highlight edge cases explicitly and explain how your solution accounts for them. This not only demonstrates your problem-solving skills but also your ability to think critically about edge scenarios. There are also several related problems that you might encounter, which can help reinforce your understanding of the concepts. For instance, LeetCode 877, the Stone Game, is a classic 2-player game theory problem that requires optimal strategies. Similarly, LeetCode 1140, Stone Game 2, introduces more complex rules, adding further depth to strategy development. Of course, LeetCode 486, Predict the Winner, is directly related and focuses on predicting the winner based on optimal play, making it a foundational problem in this category. Beyond game theory, problems like LeetCode 198, House Robber, might not involve 2 players but still emphasize maximizing outcomes under constraints using dynamic programming. Exploring these problems can help you identify recurring patterns and solidify your grasp of the techniques needed to solve game theory challenges. When it comes to alternative approaches, dynamic programming stands out as the optimal method. By defining a DP table where DP, I, J, represents the maximum score a player can achieve for the subarray between indices I and J, you can achieve a time complexity of O(n)². The trade-off here is that the space complexity also scales with O(n)², which could be significant for larger inputs. Another option is a recursive approach with memoization, which calculates scores top-down while storing results to avoid redundant computations. Although this avoids recalculations, it can still lead to a large recursion stack for big inputs, potentially causing stack overflow. A faster but less effective alternative is the greedy approach, where you always pick the largest available value. While this has a time complexity of O(n), it usually fails because it doesn't account for the opponent's optimal moves. Lastly, the Minimax algorithm is a game theory technique that simulates all possible outcomes and picks the move that minimizes the opponent's advantage. While effective, it is computationally expensive, with a time complexity of O(2)n, making it impractical for larger inputs. Understanding these methods, along with their trade-offs, will help you choose the best approach for the problem at hand. Great job! We've successfully broken down and solved the Predict the Winner problem using dynamic programming. Remember, the key is to recognize patterns like optimal substructure in game theory problems. Thanks for watching, and feel free to explore more problems to sharpen your skills. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!